Namaste. Hello, everyone. Hope you're doing good. So, today I am with an article from Science Made Simple. So, it is basically the explanation of quantum computing. Quantum computing. So, just the basics. And you can see this is a quantum computer from DOE's Lawrence Berkeley National Laboratory. So, it's a cooling system to keep the qubits, I guess. All right, DOE stands for Department of Energy. Okay. So let's read it out. Quantum computing may revolutionize our ability to solve problems that are hard to address with even the largest supercomputers available right now. Yep. So quantum computers consist of bits or qubits. These qubits play a similar role to the bits in today's digital computers. So in digital computers, like we have bits of zero and one. So what are the web pages you're seeing? What are the internet content, Netflix, like Amazon Prime? Like what are the form of digital entertainment you're consuming? Those of the form of those are like come down to bits, right? Zero and one, the combinations of it. Uh, so in quantum computing, similarly, we have qubits. Those are not zero and one. Those are not six, right? So by manipulating the information stored in these qubits, scientists can quickly produce high quality solutions to difficult problems. Um, so it does speed things up, right? And scientists have demonstrated these quantum speed ups in several applications, including database searches. Cool. Okay. So yeah, this is a new thing, right? The database searches. I did not kind of like think of it. I was thinking of like applying the applications are huge in terms of the chemical research, the molecular research, and climate change things going on. But yeah, we can kind of like speed up the database searches, right? Cool. Researchers expect quantum computing to be particularly good at calculating properties of physical systems that are inherently quantum mechanical, right? So these quantum mechanical physical systems follow the quantum computing, like the quantum guidelines, right? So that will be particularly good at calculating them, right? Okay, these applications include molecules used as chemical catalysts with, which, despite their large size, are subject to quantum mechanics. They also include quarks and gluons that clump together inside the nuclei of atoms. So remember, like the atoms in the physics class or so. So it was like so tiny, small, and inside that atom we have proton, neutron, and nucleus. So inside that nucleus we have like quarks and gluons. So so just kind of like imagine the precision we're talking about. Quantum computers may also be especially good at solving optimization problems, which involves choosing best alternative from a huge range of options, right? Okay. So remember like the travel salesman problem, which is NP-hard. Um, because we have to like keep let's consider we have like kind of cities, so we have to go to certain places and we have to find an optimal route for it. So with these classical computers, even supercomputers, it becomes like really hard because we have to keep those uh, like keep keep all of the cities or all of the places in track in our mind or like in the RAM to be able to do it, which is quite hard uh, with our classical computing. So this might be a use case in quantum computing, and I think there's a research going on at all. Okay. So the quantum computers available today are small. Yeah, true. Noisy prototypes, but the field is progressing rapidly. Yeah, the field is progressing rapidly. Every day, if you search for quantum keyword, just you'll find like many papers, many articles coming out of it, and there's like a lot of research going on. exciting research both in software thing, like software kind of thing, and hardware kind of like they're building it out parallelly, which is exciting to be. So quantum computers may soon become a critical part of computing landscape as we move beyond the cutting edge exascale computers. So um, let's, so what are these exascale computers? So they have like huge scale in it, into it, like kind of around like 10 to the power of 16 to 18, I guess. So a quick Google search would do that. Exascale computers refers to computers capable of calculating 10 to the power of 18 floating point operations per second. That's included in supercomputers as well. So quantum computing facts. Quick facts. Quantum computers harness the laws of quantum mechanics to perform certain calculations exponentially faster than today's supercomputers. DOE, that is Department of Energy Office of Science, supports two quantum computing testbeds to advance the state of art in the quantum computing hardware. Okay, they're working on software and hardware as well. I think applications of quantum computing may one day have repercussions for both science and industry. So yeah, okay. So if you kind of like use it, use it lightly or use it kind of like unknowingly, there will be like repercussions for every technology, right? So DOE Office of Science contributions to the quantum computing. So support for quantum computing research originated in the Advanced Scientific Computing Research Program in 2017. They started it out in 2017 and rapidly spread across the Office of Science. Okay. Okay. Started in Advanced Scientific Computing Research and spread across the Office of Science. The research portfolio now includes applications in nuclear and particle physics, right? It is paired and plasma science. Plasma is one of the fundamental states of matter, along with solid, liquid, and gas. It is an ionized gas consists of positive and free electrons. Okay, we have to like read. Have to like read a bit about it. The plasma state. It was first described by chemists in 1920s. Oh, okay. I have kind of like heard about it, but not exactly sure. Yeah, and chemistry and materials, of course. So it also includes improving the fundamental building blocks of quantum computers and developing sophisticated control to make the most of any group of qubits. Yeah, they are improving the fundamental blocks of quantum computing, which means the quantum hardware, developing sophisticated control to make most of any group of qubits, right? The software part of it, the hardware part of it, and computer science research that will ultimately make quantum computers easier to use, and the software part of it also. Yeah, this is like an amalgamation of like these two things go in parallel in quantum world, and they are working towards it. Cool. So this is our article for today, and I'll come up with another paper article. And yeah, see you. Have a great day. Bye.